Sorry?
Just like, right?
Yeah. No? Yeah. Okay. Should be. Hello, hello. Is that good? Okay. Buddy. Should get into the camera or something.
Maybe that's the camera.
Yeah. Okay. All right.
Okay. Okay. Hello, everyone. Let's get started with our first presentation today. We have Alex Bonsall as the first presenter. Alex is a final semester bachelor student at ITED department and doing his bachelor thesis with Safari us about ferrostatic RAM as a potential upcoming DRAM alternative. He's interested in computer architecture and more in memory subsystems and new upcoming memory technologies. And today he will present a paper from HPCA 2025 titled as PIMnet, a domain-specific network for efficient collective communication in scalable PIM. With that, let's get started.
Thank you, Mayank. So everyone, thank you so much for coming. My name, as Mayank mentioned, is Alexander. I like to be called Alex, though, for this case. And my advisors were Dr. Mohammed Sadrasati and Mayank Kabra. For those coming from the FOCA lessons, will be a great continuation of the entire lecture. So let's get straight into it. So this is my quick overview, but I'm going to jump straight into it. We're a bit late already. PIM summary. So what is PIM? So this is a typical von Neumann architecture. We have our memory bus, CPU, and DDR memory. Of course, when you access memory from CPU to the memory, you have a long latency via the memory bus. So let's try and fix that using process in memory. Because of recent many applications that require a lot of data, it would be better to do processing within the memory instead. So we can apply computation units there. Of course, there'll be a much shorter latency in that case. Benefits of this, shorter latency, as well as you can use the full utilization of the internal memory bandwidth for this. So that way we can do more quicker. And then, of course, as well, the host would no longer have to worry about simple computation operations, which can be then rather used for other more important operations. So there we go. So moving on to UpMem PIM architecture specifically. So UpMem is a commercially currently used PIM architecture. It is a combination of both regular DIMMs as well as its own current UpMem PIM-enabled DIMMs. This is actually what it kind of looks like right now. This is currently the commercially used available one. And this is what it looks like inside. So we have our chips, and within each chips, you have your 8 different banks. And these 8 different banks have got some specific internal components. You have your DPU or your DRAM processing unit, which is this green part here, which will have a 14-stage pipeline, 32-bit processor, and supports 24 threads, or as they like to call them, tasklets. There's also a 64 megabyte DRAM bank, which is where most of the memory will be written to and read from the CPU. You have an IRAM 24 kilobyte instruction memory, which is where the instructions will be stored for the GPU that will be then used for computation. And then you also have a 64 kilobyte WRAM, which is what is called a scratch pad. And the scratch pad is where you'll be the DPU will be using for its computations for in between storages and loading of processes and such. So yeah, the major drawbacks of the UpMem/PIM is that each DPU runs individualistically as of now on all on small programs. And if there were to be any communication between DPUs for the computations and such, you'd have to have a huge latency because you'd have to go all the way up to the CPU and then be orchestrated all the way back down so that the 2 different DPUs from 2 different banks can communicate with one another. This could also lead to idle DPU banks on the sidelines, which would not be being utilized. And because of all this, this paper is going to be tackling the problem of the communication between the host and the PIM, as well as the big problem of local access memory only. So the prior works that are currently that try to solve this problem, one of them is being Simple PIM from PACT 2023, done by our own Safari lab, actually. The key idea here was there's a simplified coding interface and also resembles a little bit of distributed systems. It improved the performance of PIM by 10 to 37%. But the downside here, of course, being, again, CPU overhead, which will be a recurring theme soon. Another prior work was PIDCOM from ISCA 2024. Also, again, simplifying coding interface, used a cool 3D hypercube virtualization of DPUs. In other words, basically just brought memory to the correct locations before computation would be done to minimize CPU host orchestration. The benefits here were 4 to 5 times improvements in performance, and eliminates most of the CPU overhead, but not all of it. The downsides here being mostly, of course, again, CPU overhead. Here's a quick example. Here's a baseline PIM example of some data transfers. And then you have the CPU being simplified a bit more, and again, a bit more once again by this paper. But at the end here, you'll notice that although they managed to get rid of most of the CPU overhead with all their computation and such, it still required some orchestration by the CPU, as you can see here, to host, which would then lead to a bit of latencies here. Now, this is the problem we're trying to tackle and getting rid of this entire green bars, basically. The last prior works, so the 2 prior works were software implementation. These are now hardware implementations. So you have DIMLink from HPCA 2023 and also NDP Bridge from ISCA 2024, similar papers. DIMLink, was a paper which basically added features of DIM bridges, essentially between DIMs to have interconnectivity. And then NDP Bridge was very similar to PIMnet. You'll see later in a second. But the problem with NDP Bridge was the fact that they used buffers and they didn't have any interbank communication. But the rest of PIMnet and NDP Bridge was very similar otherwise. The performance tiers were DIMLink was around a 6 times benefit, and then NDP Bridge was around a 3 times performance gain. Downsides here, again, as per usual, more CPU overhead for orchestration, and especially when it came to NDP Bridge, was bad scalability because using buffers and such, and with large data models and scaling up with large GPUs would eventually lead to these buffers being completely filled up and no longer being utilized. So it had bad scalability. So we're going to move on to PIM motivation, or PIMnet motivation rather. Here's a fun little graph that we found from the paper. Basically, it was saying that you had a baseline PIM of what UpMem could support. Then you had a software ideal, as perfect as you could get software to become, or with the overhead of sending orchestration all the way up to CPU and back again. And then here's what the possibilities of PIMnet could possibly achieve, which is around 10 times better of what the others were performing. So in other words, key insight, perfect software implementation will not outperform PIMnet. So the goal here is there are going to be 3 different types of communication protocols. You have the all-to-all, which is essentially you have, in this specific example, you have 6 different memory points, which each have data that each other require, and you have to share them amongst all each other. Another example is scatter reduce, where you have 3 different data points that have to be used in the function and then outputted to these same nodes again, and all reduce, where you have a similar thing to only to 1 node. This is a lot of data transfers within the memory itself. And the goal here is to now support these types of communications and reduce their latencies and such, using, of course, existing structures as much as possible, as well as perhaps adding some more, not much, and getting rid of as much of the CPU overhead as possible to practically none. Of course, as well, we're going to need some provided integrated software and interface for this implementation. So now getting to the meat of things, PIMnet itself. So you have PIMnet, interbank, interchip, and interrank here. We're going to start off with the interbank here. So we have what I mentioned earlier from the UpMem. You have your UpMem chip here with your banks. And now we're going to add in what's called the PIMnet stop, or what is basically just a router. And these routers are going to be interlinked via a ring structure, a ring communication using the bank IO buses. Then in the chip region, which is going to basically be the memory buffer of the rank, you will adjust the buffer a tiny bit to have all the chips be able to communicate with one another as well using DQ pins. And then when it came to the interranked channels, you'll be using the DDR buses and a small interconnect between the bus communication as well. Yeah. Oh, one little tiny detail. Although it looks like it's 4 separate DIMMs here, it's actually just these 2 DIMMs are back to front of the same DIMM, just 2 ranks on the same card. And then there's 2 cards per channel. So now we're going to move on to what it looks like inside the bank itself and how that's going to be changed up to improve this performance. So this is what we saw earlier. This is just a slightly different look of it, of the UpMem base. And now we're going to add some muxes and adder generators and routers involved. So everything that's in red is what PIMnet will be applying to the UpMem architecture. So the muxes are basically going to receive data from neighboring banks and then plugging it into the WRAM to then be used by this GPU specifically. So you have here your router and you have here your neighboring banks. And as the ring structure, as I mentioned above, it can only be your neighboring banks. And then if data would be required from bank 1 or bank 7 or vice versa, data would be flooded in through the router and then written into the WRAM, which then this DPU would be able to compete with if need be. Another option here, for example, would be interchip or interrank even possibly. and any data that would be required between a higher part of the higher level of the memory hierarchy could be sent via this MUX here. And then here's another MUX just to orchestrate all the address generators and making sure the data gets where it needs to go and such. So these are the added components that would be required within the DPU itself, or rather within the chip itself. Let's move on to the buffer. The buffer is also going to have some added components. You have an inter-chip switch, which will be added into the memory buffer. It's basically just going to connect up to the DQ pins, and it's just going to basically steal the data and throw it into inter-chip switch, and then send that data down the appropriate DQ chip. I'm going to show a little example here of a packet coming from chip 4, and it's going to go to chip 0. So it's going to be intercepted, go to inter-chip switch. From there, it's going to go redirected towards a different DQ pin, and then back all the way up to chip 0. And then within chip 0, I don't know whichever bank it's required in, and they will just go up into WRAM, and then it'll be used there for further computation. Another option is inter-rank switch, also within the buffer. Same idea. It'll be intercepted by within the DQ pin, get sent into inter-rank switch, and then from there it will be sent further on to whichever other rank or etc. So now we have to do also a bit of the software implementation for all this. On the far left, you have the baseline collective communication for PIM, which is what PIM was originally at the beginning. Up then, as you can see at the very top here, it's a bit not sharp right now, but you have the host kernel loading up individual tasks, and then the PIM kernel being tiny, so it has to have a lot of orchestration by the host again to execute, gather, reduce, and scatter these communication protocols I mentioned earlier. So there's a lot of overhead with the host here. Here's the PIMnet proposed pseudocode for it. You have the host kernel, and then you have the large PIM kernel. And then here it will take care of its own individual communication protocols. And then it will then execute these individual codes within the individual banks and such. A quick detail is the fact that when it comes to PIMnet, the entire system is a scheduled-based system, and it's very deterministic, which means, in other words, that data has to be known where it's going to be going, and it cannot be on demand. So synchronization is an incredibly important detail. There can't be any congestion. Addresses have to be known beforehand, and there can be no unexpected scenarios. As soon as one of these is not fulfilled, data will be lost or corrupted or etc. So moving on to build the code, what happens within the banks themselves, you have the poll signal. This is what was exactly the whole point of the synchronization. All the DPUs have to come into lockstep with one another and be synchronized together in order to pull off this computation. RS specifically with this one is specific for reduce scatter. It's program specific, and it's just uploading the WRAM to the MRAM to make sure that you get the correct data that's required for this computation in the scratchpad. The wait command is a command that is required for if you need to go outside of the interbank region to the inter-rank or inter-chip to be able to communicate with more DPUs in order to do a larger computation. So you have to wait to orchestrate where all the data is going to be going. You have to figure that out. The ready and start. So once all the DPUs are ready to go and they've all been put into lockstep and all their data is correctly set up in the correct locations, they'll be sending out a ready command, and all DPUs will then, once they're correctly good to go, they'll send a start command, and then the program will execute. There's a scope, which in other words basically means the amount of DPUs you require for a computational program. If a scope were to be larger than the bank it's currently in, or within the inter-chip, within the entire chip, larger than the entire chip, it would then start sending these ready signals outside of the chip to the inter-rank region and asking other chips neighboring by to be like, hey, we need your DPUs as well for its computation power. And then that's where the wait command comes into play, because you need to start scheduling data between chips and such. And then once all these have been, once the scope is fulfilled and the readies have all been ready to go and such, the work would be executed, and then, the start would be executed, and the program would go along. So how does this improve? We have I'm going to take an existing example from the internet, which is just a simple DDR4 2933 Core X Intel series chip. It's got around 94 gigabytes per second of data bandwidth within the entire host. And then per channel is going to be around 23.5 gigabytes per second. And then I'm going to compare it now to PIMnet. So we're taking a estimate of around 0.7 gigabytes per second per bank of bandwidth. We're going to take that to the chip level, which is going to be 2.8 gigabytes per second, divided by 2 for the amount of banks, because every second chip has to share an I/O interface. These chips are then going to be multiplied by 8 to get a ranked level, which is going to be 24.4 gigabytes per second. And as you can tell, the rank and the channel between the existing and the current PIMnet is more or less the same. Of course, this is channel, so there could be 2 ranks within it, but you can estimate basically the fact that this is going to be half or doubled the amount of bandwidth as it would be with existing systems. Another cool little detail would be the fact that you could have an aggregated ring or reduce algorithm, which would then basically make it so that every single bank goes in a clockwise fashion to send data to one another. And you can get maximum output bandwidth for 180 gigabytes, basically, which is pretty neat. So really quick, I went through this pretty quickly now. I just want to summarize real quick for everyone, so no one's lost. Basically, PIMnet is a data management, and the propagation is entirely dealt with in memory. So all the data management is dealt with in memory, and it's all being propagated in the correct locations, somewhat similar to distributed computing. It's also utilizing the complete bandwidth parallelism within banks. So it's using all the built-in connections, which means it can use the full bandwidth possible out of it. And it's just a very much more efficient way of moving data around. The only downside perhaps for PIMnet is the fact that all communication has to be deterministic, and you can't do it on the fly or on demand. Little summary image on the left here, and on the right here is a cool little diagram showing what PIM would be like, or UpMem in general, basically without any implementation, where you can see that you get double the latency or double the time to do the computation because it has to communicate with the CPU for orchestration, in comparison to PIMnet here, where everything's dealt with in memory. And then the time is reduced by half, essentially. Okay. All right, so results and performance. Quickly go into methodology beforehand. We're going to compare PIMnets against its UpMem base, as well as the 4 different other papers that I mentioned prior. And then these comparisons are also going to be mentioned mostly with the all-to-all, reduce and reduce scatter performance programs. And then it's also going to be compared with 9 different workloads. And then in the very endish, I'm going to be explaining one other benefit, which if you were to be using a different type of PIM architecture, not UpMem, but GDDR6 AIM, and how that could even improve the performance even further. So moving on to these 2 first. So all reduce represents 83% of total execution time. With PIMnet, this reduces down to 5%, and it will basically result in a 5.6 times speed up, which is pretty great. When it comes to all-to-all application, the more DPUs PIMnet has, the better this performs. So it scales really well. It gets better with time, or better with more. And of course, unlike the other papers, it has no overhead of the CPU, so it gets much better scalability. So as soon as you get into high data, larger data blocks and more DPUs, it gets better and better. As you can tell with this one graph specifically, all-to-all, you have your NDP bridge, which is the orange graph here, starts off pretty decently, but over to 256 DPUs, it gets even worse and not better, unlike PIMnet, which is yellow, which only improves. And then DimLink here is relatively consistent across the board, but again, still worse than PIMnet. Here's some more examples. So again, P here being PIMnet, D, N, and S, and B being baseline, the other 3 being like the in-between proposed papers and such, across the board of all the different types of workloads. PIMnet in most cases outperforms, especially these red dots. Especially here, which I think is quite funny, is off the scales, which I think is quite nice. In some cases, it doesn't really improve much, but neither do the others. So I'm assuming this is not a very data-centric problem or workload. Yeah, so just to show it's doing quite well. Around 11.8 times improvement over base PIM. So other points to point out is PIM banks with the added features that I mentioned earlier. It's going to increase the area consumption by 0.09%, practically nothing. And increase the power consumption by 1.6%. With the inter-rank and inter-chip switches, which are these 2 switches I showed largely in the buffer, going to extra consumption of 0.013 millimeters squared and 17 milliwatts, which sound like a lot, but if you compare it to the NDP bridge buffers that they were using in their whole proposal, still a lot better. PIMnet system latencies. So I mentioned earlier that perhaps the synchronization, it might become a problem. But if you compare the synchronization for the whole lockstep situation and making sure all the data is in a correct location doesn't take long, around 6 DPU cycles, which is around 15 nanoseconds. And compared to the smallest problem that PIMnet can deal with, which is the smallest message size of all reduce across all its GPUs, takes only 1,000 cycles, which when you compare it to is negligible for the synchronization point at least. And even if the bandwidth, bank bandwidths were to be much worse, so this point here, if this was were to be 0.1 instead of the 0.7, PIMnet would still outperform DIMLink by 3 times. So scalability and what I like to call the piggybacking on improvements is basically that PIMnet can be easily added to any newer or updated PIM architectures and DIMMs that come out in the future. It's got great scalability, so that's not a big problem when it comes to future proofing and such. More DPUs, the better. And especially when it comes to different types of PIM DIMMs, it could become better. For example, here GDDR6 AIM versus UpMem is 160 times better. And this could theoretically improve PIMnet by 40 times from what it currently is because of the multiply and accumulate units that could be added into it. As well as it works very easily with the next generation UpMem, which will get floating point operations. So it will just scale very well into the future. So conclusion. Consistently outperforms the other PIM implementations, has 11.8 times improvement over baseline PIM, which is going to be UpMem. Scales very well, has basically no CPU overhead except for just execution or PIM kernel initialization at the very beginning. And it also has just practically negligible power and space consumption. So that's basically the entire presentation. I'm going to be moving on to the strengths and weaknesses of the paper now quickly, and then on to the discussion part. So the strengths of the paper is it's constantly thinking of the future and it's got easy scaling possibilities and such. The understandability of the paper was simplistic wording, so it wasn't you need like a crazy degree in order to understand what the hell was going on, which is great. And had a good structure, especially, which is very helpful for such a paper. And of course, it's a very interesting paper, so it really helped motivate you to keep reading and such. The weakness of the paper is perhaps like a double-edged sword, of what I mentioned earlier, the simplicity of the wording, because then, of course, some points were unclear. Some of the imaging was a bit unclear, which I showed you earlier with the DIMMs being double-sided and such. It was a bit confusing why that was. And yeah, and then they used always the most optimal configuration for their testing. So this is not necessarily going to always be the case when it comes to real life use of how many GPUs you'll be using. So it could not outperform as much as it should, but yeah. And the routing specifically, when it came to the routing protocols for the PIMnet, was very difficult to follow in my opinion. Mostly because there were no concrete examples from start to finish of how it all works, the communication and such. So that's something I think the paper could improve on to make it a bit more understandable. So let's move on to the questions. Before I actually do start the questions, does anyone have any understandability questions of what I mentioned throughout so far? No, okay. So I'm gonna first move on to a scalability question of what would you think would happen if, as of right now, we have 8 banks per chip. What if we were to increase it to 16, 32 banks per chip? Would that help? Not bring much. Perhaps a different interconnect structure. As I mentioned before, it was a circular interconnect between all the banks. Perhaps a full interconnect might be better. Maybe on the crossbar with an interchip, maybe there we could change something up. Maybe be completely interconnected there as well. Who knows? And then why only interchip and interrank and such? Why not inter-channel? Anyone have any ideas? Doesn't have to be something too crazy. It can just be like, do you think interconnect would be much more performative? Because right now, inter-ring, you have to propagate data between each bank until you get anywhere. Yeah, what's up?
Just dumping the number of banks to double the
Interbank latency? Potentially. Oh. I mean, yeah, if you were to still have the ring.
You still use the ring buffer.
Yeah, then for sure, it could also double. Yeah, that's definitely true, depending on where the data is going, for sure, absolutely. But you have to also consider that with more DPUs, it scales better. So perhaps it will cancel out. But no, it's a good point, for sure. Perhaps a different structure instead of full interconnect. Any ideas there? That's why you had your hand up, was the same thing as him?
Yeah, but maybe like a
comment on maybe I can comment on the interconnect structure. So if we decide to do a full interconnect between all the ranks or chips, then we will decrease the latency, but then we will increase the surface of the chip. So we will need more surface area.
Yeah, great. So I was actually going to point that out as well. So my suggestion was just do every second connection instead of full interconnect. Maybe you just one extra hop is not that big a deal. It's not too bad. You also will save on some consumption of area and power, perhaps that way. Utilize the same cables a bit more, so they're not just a load of redundant cables that just not used as much. Also, more the better, of course, when it comes to DPUs, but you have to also consider into it cost and such and scalability. So yeah, we'll have to see about that. And if you were to go larger chips and such, you also have to start thinking about adding larger buffers to take care of all the DQ pins and such, which would then, well, depending on the memory type you have, memory architecture you have, you might have to add more stuff on top and such. So yeah, here's my little suggestion of how it could be added. I don't know. So security question. This is my favorite question. If DPUs were to be hacked, typically not in the first case when it came to UpMem, but now that they're all interconnected because of their sharing of memory and such, do you see any problems with this? Because typically it was very secluded, very individual. There wasn't much that could happen if one DPU would be hacked. Now they're all interconnected. They can all be sharing data amongst each other. They can propagate. How do you think that could affect it? Like, is there a way we could solve this by somehow? And also my other point was, would the CPU or the host ever know the DPU's been taken over somehow? Because they're quite separated from one another. Any ideas there? Yeah, I'll start with you first.
I'm not sure if I understand what you mean by hack, but if one is
Well, I don't know.
controlled by
Maliciously somehow taken over.
yeah, someone took over one, he can read the data of all of them.
Yeah,
because they are interconnected, and the CPU wouldn't notice because they have their interconnection network. So it would be worse, but I don't really know how they would be hacked without the CPU noticing, because isn't the CPU the one that schedules the programs? And
yeah, but perhaps there was some sort of malicious data that was somehow stored on the UpMem chips, and then once the data is being propagated around, perhaps via that.
Okay.
I personally don't know myself.
Yeah, okay.
I'm just throwing out the idea out there. I'm not very good at the security situation when it comes to computer architecture, but I thought it'd be interesting to hear what other people have to say about it. But yeah, no, for sure. Do you have a point as well?
I mean, if it were to be hacked, they can issue a malicious, synchronization thing. Maybe if the DPU chips are hacked, they can break the synchronization.
Yeah, for sure, absolutely.
And maybe issue or share garbage data around the
And I was also thinking, if you were to have some sort of like virtual pages connected to it, and you somehow manage to hack one DPU and then copy paste your malicious program into a specific directory, where then you would have virtual paging saying that you do have read and write and execute commands on it, then perhaps via that you could get into kernel access and such. As a theory, I have no idea. But
yeah, I mean, possibly. The only way to prevent this, I believe, maybe the DPUs, when sharing data in the circle, they can also, issue some message authentication codes such that, such that we know who issued this, who sent this data to the circulation with the signature. But then you need to do some key management as well as.
Sounds like a lot more overhead as well.
Because if we scale the chips, then we need a lot of more, key managements, keys.
Mm-hmm.
And that will make also
seems like a lot more extra work.
Yeah, more difficult to manage.
No, that's also a good point. I didn't even think about that one. My suggestions were using dummy systems for the DPUs. So essentially, you would initialize your kernel code, your DPU kernel, and then once the entire program has been executed and fulfilled, then the CPU comes to all DPUs, flushes them out completely, flushes out the WRAM as well, the scratch pad, so that nothing could be malignant staying over, and just having a clean slate every time. What's the suggestion I have? Maybe you didn't have to do it every time, maybe every second, third time, who knows, but yeah. Also, I thought was quite fun was that UpMem theoretically already has a RowHammer mitigation, which, if I'm not mistaken, I read the paper and it said that Safari was requested to write the paper about this to theoretically solve this problem. I don't know if anyone's here who's actually written that paper or done anything about that research, but it's what I read, so I thought that was quite fun. Moving on to discussion 3, improvement questions. What if we had a direct pipeline to the MRAM? So just skipping the WRAM completely in the first place. So this is what we have currently. And we said there was a scratch pad here, which is what we're using basically for whole in-between processing points and such, just saving in-between data and such. Would it be better to have this computer pipeline go straight into the MRAM, which is the one that the CPU would be reading from, instead of having this scratch pad in between points? Like, do you see any problems with this? Do you think it would be improving performance, decrease latencies? What do you guys think? Like, I don't know, just straight in. Do you want to pass the microphone over quickly?
I assume it may increase latency because like it seems like the MRAM is larger, probably slower. So for example, if the compute pipelines, like if the operations are dependent, let's say it has 11 stages and in each stage you need the computation from the previous one. You probably, I mean, now I assume you write to WRAM, then read, then write to WRAM. But if you were to go to MRAM, probably the round trip would be longer, slower.
Possibly, yeah. Possibly, yeah. Yeah, so basically the WRAM is essentially kind of like the cache for the compute pipeline as well. So you think it'd be mostly just higher latencies with communication between the two. Yeah, I mean, you could also just, I mean, don't think of it as like physically far away from each other, because this would be easily just shifted over here, potentially. But yeah, but reads and writes maybe from the MRAM because of just how it's architecturally set up might be a fair point, yes. So specifically for me, I thought a big problem would be if the CPU were to try and access data from that MRAM as the DPU is currently writing or doing programs with that current memory. You could get some very dirty memory from it. So that's already a CPU problem with that, just reading dirty memory. But I would assume it would probably likely increase performance, but if it would be worth it for the dirty memory, who knows? Perhaps if you were to somehow figure out that you schedule the entire thing correctly, the CPU and such, that it would only ever access the MRAM once the computation is being completed, then maybe it'd be fine. But then at the same time, if there were to be any details within the MRAM that the CPU would need now, for example, as the GPU is doing some sort of computation, that would be inaccessible at the time. Or perhaps with a lot more thorough software implementation, maybe you could separate that out and such. But yeah, let's see how much time I have left. Okay. So my last question is going to be a maintenance question. So I thought this would be a quite interesting question because the last, I think it was 2 papers or presentations, had a maintenance type idea to the entire memory and such. So what do you think is a possible maintenance that can be done within the memory now that we have pretty high compute processing units within memory itself? Perhaps there's some sort of direct taking care of memory within the individual upland banks and such. So you have, as before, you have your whole memory array here. Maybe we could take care of refreshing a bit better, the refresh management a bit better. We can maybe take care of some sort of durability problems, perhaps. Yeah, any ideas? Yeah, Shiver.
So maybe while we're computing on the data that's reloaded into the WRAM, we can in the meantime perform the maintenance of the kind of copied rows in MRAM.
Yeah, probably.
Because we're kind of operating on that, and then that can be taken care of in the background and overlapped latency.
I think it's probably definitely an option. They're all very theoretical. I have no idea how to implement it myself, but I think these are some pretty cool things you could definitely do. Yeah, what's up?
I thought maybe we can modify the instruction set architecture to add like a new refresh command, which we can issue from the DPU side, so that we basically generate the refresh command, but now we're kind of like before the primary processing unit was the CPU, now it becomes the DPU, so it kind of shifts the master-slave system from CPU to DPU.
Yeah, I think that's a pretty good idea. So I had this one really cool idea where, since you have a much smarter processing unit now next to memory, you have that individual processing unit learn its individual MRAM banks, and then eventually learn its arrays and selectively turn off perhaps dead cells. So it could even potentially increase longevity of the whole memory as a whole, or at least UpMem at least, which I thought would be a pretty cool idea. And then I was saying they could run their own maintenance during wait cycles and such. So during wait cycles, when they have to wait for all the orchestration to be figured out of where memory is being sent back and forth, some of the DPUs could be taking care of their own maintenance, making sure that all their cells are refreshed and ready to go and such. So yeah. I have one last question, which I think is a bit difficult to answer, very theoretical. Is there a possibility to make the system asynchronous? So as of right now, everything's synchronized, everything's in lockstep. You can only run one program currently in the entire memory at a time. And then once you finish that execution, you have to make sure everything's in lockstep again, refigure out the whole programming, and then set up a ready and then start commands all over again. Is there a potentiality to make it asynchronous so you can run two separate data management programs simultaneously, side by side? What do you think would be required? How would things have to change? And keep in mind that the one paper I mentioned earlier, which scaled very badly because of buffers. Because, yeah, that's an on-demand system, if you guys know what that means. So how do you think this could possibly work? Very theoretical, no idea. So I had one small idea. It was called an on-demand system. And it's how in the internet it used to work. So in the internet, we used to have a scheduling-based system as we do right now in PIMnet, where everything had to be scheduled of which data packets we sent when and such. It made it very reliable, but also made it very slow. On-demand system, basically, you had to implement more buffers into the internet and such that you could just send out data whenever you wanted to. And if there was ever an overflood that the throughput couldn't hold or accept because the throughput was completely filled out, the buffers would then accept these extra data points, save them, and send them out once the throughput has been decreased a bit more. Here in this situation, we'd have to add buffers once again into PIMnet, which, as we mentioned earlier, would be difficult to do because of the scalability problems and such. But if you were to somehow solve that issue and then figure out an on-demand system for the entire coding part to it, the entire application software part to it, you could potentially get even more performance out of it by having a lot of parallelism involved and such. And also the improvement of PIM architectures and such, new PIM cards and such coming into play and such. The on-demand system could even make it more, be able to execute more complex code within memory as well. So yeah, that will be my entire presentation about PIMnet. I hope you guys enjoyed. Hope you guys learned something. Thank you for listening.
Short comment. Anybody else? Everybody's busy. Thanks for the presentation. This was a good presentation, and this is a very good topic, I think. I like this paper. I think we need more mechanisms to enable better communication across computation units that are outside the CPU. Yep. Because that's one of the bottlenecks of offloading more applications, as this paper also showed. Yep. So I think there's more to be done in this area for sure, especially optimizing the network, etc. Yeah.
It's gone far, but there's a lot of, I feel like with the paper right now, we're at the beginning of where the internet used to be.
Exactly. Yes.
And then we just have to figure out these next couple of details, and then it can become something amazing.
Yeah, definitely. I mean, the UpMem system initially doesn't have any communication because they had cost restrictions, but I think we need to have more and more. And to answer your comment about the work that we did, I mean, we work with UpMem on analyzing their PIM, but also on RowHammer, which was a fun COVID time project. Let's say it was led by Girai, who gave a lecture on memory robustness. So it's the analysis of their silver bullet technique. We have a 40-page report on archive, if people are interested. I think that's probably what they referenced.
Yeah. I was trying to find it on the Safari website, but I couldn't find it at the time. So I was like,
Yeah, it's online. It's on my website. Okay, it's online on archive also. It's a very rigorous work analyzing the security guarantees. In many ways, I think what they have developed resembles per row activation counters that we talked about today in FOCA, if you're here, or in RowHammer, I think. But it's a more general mechanism, and we had a generalized security proof for that sort of mechanism and some performance analysis. So if people are interested in that, they can take a look.
Thank you.
And I guess if no one else has any comments, we can take a break, a full break, I think 15 minutes, and no? Okay. Yeah, okay. And then we're back for the second presentation.
Okay. Thank you.
Should just leave it.
I didn't even get the watch battery and that. And then wouldn't charge. So I mean I bought another one. Yeah. But it's this kind of I don't know.
Yeah, that's. Do you have like type C?
No.
No.
No, it's kind of like this.
Yeah, so the question would be
I get someone's schedule.
Okay, I mean, yeah, the conversation online or we do online or it's just a mistake or I didn't know that.
No, it's online.
Okay.
I think it works basically better online so that you can get
Record like the meeting and then I okay. Okay, sounds good because I already did that. So I assume I should have
so I guess you have it.
the slides. I just finished it today. Yeah. Maybe I can also like create some like the draft of the site, but don't have like the draft. Maybe I can before you don't want to.
We don't usually have.
Okay, okay, it is good. I never used it.
I was working.
No, I mean,
But you don't have to see it. But our second is supposed to be business science.
for now, probably just like no. Like I just start maybe
I came in here like super relaxed, to like calm down, and then we're like, and now it's okay. Now I go to start. Yeah, that's why I had to take because I knew this was going to happen. That's the only It was insane. I like in the same student.
See each other every day. Yeah. Don't worry. Are you watching today? Yes. You can use the yesterday was our school. That's the plan. And today is yesterday I was rooting my heart off to myself. Yeah, but it's like you know, I've been playing a place with and I was watching this TV. No, I was really depressed. We were screaming, shouting, everything. No, I'm just. Yes. I have never been. Are you watching it here? So you're like you'll be watching Greek. Yeah. Costas, do you know like Greece, like World Cup football? Well, if Turkey manages to qualify, it's the first time in 20 Oh my God! It's with Spain, Georgia. That was what it's like qualifier. And what is it, George?
That's very normal. Just being going process. But when I'm nervous and when I feel like I've lost time because of issues,
I hope.
I try to think of practice every day once I go to the questionnaire. I was on my last quiz, 10 minutes left, an hour, and I was like,
What's the check? That's oh my God! That's the most free group I have ever seen.
that's right. Hit point for fair.
But overall,
Denmark. Oh, Denmark.
I was concerned about my.
Scotland was not bad. Really? Yes.
I didn't know I was like,
Bro, you're just the best.
although I will admit that
Someone
crouching
will
is
say
part
Oscar.
of it.
Some people just have goals and then no, but that's the thing. I remember the last the Euro championships and then you cross
I went there for that. Fair, okay, yeah.
Oh!
So he's brought that I hope you go.
Like the new process. We have this local name server, which yes, I think that's what you are doing. So we wait to receive the therapy and by setting up the connection, no, that's the one. I mean, I don't know where they go. Yeah, I was but yeah, I mean, right now, we have the process manager
Trying to do stuff. No, this one is yeah, I see.
It's also the whole way.
Just say German.
Test 1, 2, 3.
Hello, hello.
So other than that, did you check the
Yeah, it works.
Yeah.
Because on the issue, it's the only
Yeah. Should we start?
Yes.
Hello, everyone. Welcome to the second session of today's lecture. So Christian will present functional complete Boolean logic and real DRAM chips. Christian is a second-year master's student in computer science. He earned his bachelor's degree from Germany and is mainly interested in high-performance computing and cryptography. Please.
Thanks, Ismail. So yeah, I'm presenting functionally complete Boolean logic in real DRAM chips. It was first presented last year at HPCA by Ismail, but today it's going to be presented by me. In terms of executive summary, so this is a processing using DRAM paper, and we're trying to do certain DRAM operations in real existing chips that are on the market today. So we're not trying to extend the circuitry, but we're trying to do operations which we can do on existing chips. And prior work has already demonstrated certain operations like the majority 3 function, and built from the majority 3 function the and or function for 2 inputs. But the problem is that the majority 3 function on its own is not functionally complete. So you can't express arbitrary Boolean logic using the majority 3 function. And the and or functions built from the majority 3 function are only 2 inputs. So the main 2 points addressed in the paper is to extend the set of operation to be functionally complete by introducing the NOT operation in real DRAM chips, and to extend the 2 input and OR operations to up to 16 inputs. So the key idea to tackle these problems is to use the already existing sense amplifiers to basically, and the NOT gate that is contained in the sense amplifiers, to do the NOT operation in chips existing today, and to use the comparator function of the sense amplifiers to do higher input and OR functions. And the results are quite promising because most chips on the market today can already do the NOT operation as well as up to 16 input and OR operation, as well as their negation and OR operation with reasonably high success rates. So before I will talk a bit more in detail about the key ideas, I want to start with some background. Yeah, we've seen this multiple times to now. So a module consists of multiple chips. Each chip is basically a stack of banks. And each bank is basically, yeah, a collection of subarrays. And the important part for this paper is that the subarrays share common sense amplifiers. So the sense amplifiers are used to sense the charges in the rows. And the important part here is that one sense amplifiers, this is called the open bitline architecture, is normally connected to 2 subarrays. This is due to space reasons, because the sense amplifiers are normally larger in physical size. than an individual cell. So what is done here is that two neighboring subarrays are basically sharing one sense amplifier, but only every second column of the subarray is connected to one row of sense amplifiers, and the other column is connected to the sense amplifier above or below. But the important part here is that basically there's already a NOT gate connecting two neighboring subarrays. And a bit of background how activating and sensing cells normally works, so we can know how to break it and use it for the NOT operation as well as the AND and OR operations. So normally, if you want to read the cell, you first have to activate the corresponding row, and you do this by sending the activate command, which will basically connect the cell to the corresponding bit line. So what you see here is one cell basically from the top subarray, one from the bottom, connected by the back-to-back NOT gates, which is the sense amplifier, and the squares here denote the voltage level of the corresponding bit line. So in the initial state, it's important that the bit lines are pre-charged. So normally a pre-charge command has been issued before. And what happens now when we activate a certain row, which will assert the word line, is a process called charge sharing. So some of the charge leaks onto the bit line and perturbates the bit line voltage a bit. And what will happen next is the sense amplifiers will get activated. And what the sense amplifiers will do is basically amplify the difference in voltage levels across the sense amplifier. So the bottom bit line is still charged at the pre-charge level of VDD over 2, so half of the operating voltage. But the top bit line now has a bit higher of a charge level because the cell we connected to it leaked some charge onto it, and it was a logical one, so it had some charge initially. And once the sense amplifier got activated, it basically drives the top bit line to the extreme of full operating voltage and the bottom to 0. And this was it for the activation. Now we can read or write to the row. But before we activate the next row, we have to pre-charge it again by sending the pre-charge command, which will just set it to the initial state again. So this is the normal operation. And now the key ideas of the paper is basically to not do the normal operation, to implement the NOT and the AND or OR operation. So the first key idea introduced in the paper is the multiple row activation. So normally we activate one row after another to read or write to it, but the paper manages to activate up to 16 rows in one of the subarrays and 32 rows in another subarray by sending a sequence of activate, pre-charge, activate commands that don't follow the recommended timing parameters by the manufacturer. So it basically breaks the DDR4 interface by sending these commands with violated timing parameters. And the result is that multiple rows get activated simultaneously. That's already an interesting fact, but to build something useful from it, the authors basically use the NOT gate in the sense amplifiers in order to basically do a row copy between sense amplifiers, but during the copy negating it. So instead of activating the rows simultaneously, what they managed to do is first activate the top, which will then get negated, and then basically add the bottom rows to it. So the negation of the top row is stored in the bottom rows. And the third key idea introduced in the paper is to basically use the comparator function of the sense amplifier, which I just showed in the normal operation. So the sense amplifier senses both bitline values and amplifies basically the difference. So if one of the bitlines is higher, it will be driven to 1 and the other to 0. And the other way around. To basically implement an AND function or an OR function, it depends a bit on the reference values. So the key idea here is that we have a compute subarray. So one of the subarrays is storing the operands that we want to compute on, here X, Y, and Z. And the other subarray is storing some reference values, which the operands are compared against. And depending on these reference values, we can basically do the AND as well as the OR function. And the opposite result will be stored in the reference subarray in the end. But we will see it in way more detail in a second. So these were the key ideas the paper presents, and they wanted to evaluate them on real existing chips. And so they bought a bunch of these chips and used the DRAM vendor infrastructure from Safari to precisely control the timing the commands are sent to the DRAM module. We've seen this also in past presentations. And in terms of the chips tested, they found that SK Hynix chips could do both of the operations they thought about, while Samsung and Micron could do only one of them. So Samsung could only do the AND and OR operation, and Micron could do none of them. And the hypothesis here is that the Micron chips just drop all the commands that come in if they violate the timing parameters. So we are violating the DDR4 standard by issuing commands basically faster than they should be issued. And the Micron chips probably just drop them. And a similar reason exists for Samsung. So this whole paper basically focuses on SK Hynix chips mainly. So yeah, this is the key ideas as well as the experimental setup. And now I want to discuss the key ideas in a bit more detail. So let's start with the neighboring subarray multiple row activation. So as I already said, the key idea here is to craft a special sequence of activate, pre-charge, activate commands that don't follow the normally required timing parameters. So normally you have to wait before activating a row and pre-charging it again for the charge sharing and the sense amplifiers to do their job. But in this paper, what they did is they first activated one row in the top subarray. Then they issued the pre-charge command very fast after it. So one DRAM cycle basically after it. And this basically stops the process of activating the sense amplifiers. So only the corresponding word line got asserted. And now the trick happens that the pre-charge would normally disassert or deassert the word line. But because the pre-charge couldn't finish its job and not enough cycles passed, the next activate command will also activate another row. But it's important to note here that even though we only sent 2 activate commands, more than 2 rows could get activated. And this is due to the structure of the row decoder. It wasn't discussed in more detail in the paper. It's more like an experimental observation. But what they saw is that for some pairs of row addresses, up to 16 rows got activated in each of the arrays. And to test what row addresses trigger what activation pattern, so how many rows get activated just by activating these 2 rows, what the authors did is they just iterated through all the row pairs in 2 neighboring subarrays, issued this sequence, and then it should activate all the word lines and connect them to the sense amplifier. And then if we issue a write command, we can basically read afterwards which rows have been written to, right? So using this, they could then scan all the subarrays to see which rows have been activated by this, this pair of rows that got activated initially. And the main result they achieved is that there are 2 distinct patterns of activation. So either in the top subarray and the bottom subarray, n rows get activated, so the same number of rows get activated in both subarrays, or the second subarray or the bottom subarray has the double amount of rows activated. And what you can see here on this plot is basically the coverage. So how many of these row pairs one could activate result in what activation pattern. So how many rows really get activated. And you can see that, for example, the 16 by 16 activation pattern, so 16 rows got activated in the top and 16 got activated in the bottom, is the most likely here across all the chips tested. But also there are these n to 2n patterns where 8 rows get activated in one and 16 in the opposite. And all of this is due to the row decoder structure. At least this is a hypothesis. But now we know how to activate multiple rows across 2 subarrays, but we want to do something useful, right? We want to come up with the NOT operation basically to have a full set of functionally complete operations in existing DRAM chips. So the key idea here is that instead of violating both the timing parameters between the activate and the pre-charge and the next activate, we wait for the first activate to finish. So let me walk you through a timing diagram basically to show what is happening on the cell level. So we sent the first activate command, which will assert the bit line, connect the cell to the word, assert the word line, connect it to the bit line. It will perturb the bit line, the amplification process will start, and we will wait basically for this process to finish before sending the pre-charge command. So here we follow the normal DDR4 TRAS, so the timing parameter between activation and the next pre-charge command. So what we get is basically a steady state where the sense amplifier is driving both bit lines. So it's now in a constant state, basically, where the sense amplifier can hold the voltage levels of the top and the bottom bit line. And because the cell we connected was at the logical 1 level, so at a fully charged, so voltage on the operating voltage, the bottom will now be basically at 0. Yeah? And what we will do now is do a similar trick than before by sending an activate command directly after the pre-charge. The deassertion of the bit line cannot happen, as well as the bit lines are not pre-charged yet. And basically a second row gets asserted also. But because of the sense amplifier already doing their job, the cell will just decharge because the sense amplifier is driving the bit line. So there is no perturbation of the bit line because the sense amplifier is driving it, basically. So so when it's done, basically what we have achieved is negating the top cell into the bottom subarray. So that's quite nice. So that's an idea first. So the authors validated it on the 256 chips they had in the lab. And what they saw is that depending on the number of destination rows you activate, remember we have these activation patterns where you can activate more than 1 row in the bottom subarray or the top subarray. they saw that for a larger number of destination rows, actually the success rate decreases. So this operation doesn't always succeed, but for a small number of destination rows, here up to 4, it almost always worked on the cell level. So what you can see here is basically for each cell they tested, how many times of 10,000 tries did it actually do the NOT operation. And the hypothesis here is, for why we see this decrease in success rate, the more cells we connect basically, is that the sense amplifiers are built to drive one cell in normal DRAM operation, right? Normally you just connect one row to the sense amplifiers and it drives the cells. But now we connect 32 cells from one subarray and also 16 from the top subarray. So it has to drive 48 in the worst case. And at some point it will just collapse because it's not built for driving that many cells at once. At least this is the hypothesis the authors gave. So, right, there are a bunch of other results. I can't discuss all of them here, but one of the interesting results is that the success probability, so how likely is it for the NOT operation to succeed, heavily depends on the physical location of the rows. So what you can see basically here on this plot is how likely is it for the NOT operation to succeed on an individual cell level, given that it's far, middle, or close from the sense amplifiers. And as the matrix, because we have 2 rows on the corresponding opposite sides. And we see that certain patterns work a lot better than other patterns. And the hypothesis here is this is because of a concept called design-induced variation, which basically is also the reason for why cells farther away from sense amplifiers have higher access latencies. Because of the electronics and the resistance between the sense amplifiers and the cells getting larger and so on. And it also has an effect here on how well the NOT operation basically works. These were 2 of the results the authors obtained, but it's an experimental characterization and analysis. So they analyzed a bunch of other parameters that could affect the success rate, basically. They looked at the temperature, the speed rate of the chips, the density of the chips, and so on. And it's all in the full paper available on arXiv. So, yeah. Let's go on to basically the last operation that they managed to do, which is here the AND or NAND NOR operation. I put them under 1 point because they're very similar in how they work. So until now, in previous work, they only had 2 inputs, but now we're trying to scale it up. We've seen that we can activate up to 60 rows, but for just the illustration, I'm going to show you how to do a 2-input AND, but it nicely scales for up to 16 inputs, depending on how many rows you activate, but you will see soon how it works. So here we're trying in this visualization, trying to compute the AND of X and Y. So we have 2 cells called X and Y, and a pre-charged state where the bit lines are at half of the operating voltage. And we have the so-called reference subarray. So one of the subarrays, we store some reference values, which we use to compare the operands against. So if you visualize the AND function, it's only 1 if both of the inputs are 1, right? So the comparator will say, basically, when we connect all of them using the multiple row activation, so we'll activate all the rows simultaneously, and then the sense amplifiers kick in. What the sense amplifier would see is, hey, we have a bit line here where the voltage of the bit line is basically the average of X and Y because the charge shared. And in the top, we will have the average of 1 cell and a half cell. So you might ask how we get a half cell. There's actually another paper called FRAC DRAM, which introduces a concept of getting half charged cells in DRAM. So normally you only have a logical 1 and a logical 0. So you write a 1 or 0. But they managed also using a similar timing trick to basically get half charged cells. So this is an assumption for the paper that we have this reference subarray, which we basically written to before we perform the AND operation by using this FRAC DRAM, fractional DRAM, basically, idea. And then what will happen is that once we compare these 2 values, only if the X and Y will be 1, basically the sum of them or the average of them, which is the bitline voltage at this point, will be larger than 1.5, right? So in this case, what will happen when the sense amplifiers finish their job is that in the compute subarray, we'll have the result of the AND operation. So we have 2 1s written here, and the negation basically in the top subarray, because remember the sense amplifier always drives the 2 bit lines at opposite values. That's his job, basically. So we'll have the result of the NAND in the top. So this was the example for X and Y equals to 1. If it's not the case, obviously the bottom X plus Y will be smaller than 1.5, and we will get the opposite result, right? And this was a 2-input AND, but I hope you can visualize in your head how it scales up to more inputs. So we just add the reference array with more 1.5 cell, and then we can activate up to 16 inputs. And for OR, we can discuss it a bit more in the discussion, but you just need different reference values, basically. So in terms of the results achieved, it's the opposite in terms of number of operands than for the NOT operation, which is interesting. The more operands you basically use, the more reliable the operation gets. And one thing to know here is that the authors basically, to come up with this plot, they randomly put values in memory. Yeah, so they randomly initialized all the cells. And there's only one problematic data pattern for the AND operation, which basically always fails, which is the all-one pattern. But the more operands you have and random initialization, basically, the less likely does this pattern become. So the hypothesis for this plot is basically that there's only a certain data pattern which is problematic for the AND, which triggers less likely with more input operands. And in this plot, you can basically see the problematic data pattern. It's a bit confusing, so let's focus on the top left, which is basically the plot for a 4-input AND operation. And the plotted is the success rate of the operation, depending on the number of logical ones in the input. So you can have 4 inputs, and you can have up to 4 logical ones. So the all one input is obviously the problematic input for this case. And the reason for it is also not too difficult, because the reference values were also almost 1, right? If you remember, it was all ones except 1/2 cell. So if the other value in the compute subarray is also almost 1, the voltage difference across the sense amplifiers is minimized, right? And we know that there exists stuff like process variation and stuff. So if one of the cells maybe has less capacitance or is already lose some charge, the comparison might not go well because some charge already gone, and the whole operation will fail. Same you can observe for higher input operations. And the process also starts a bit earlier because the average of 15/16 is also very close to 1, right? For the OR operation, it's the exact opposite, because the reference, I didn't show you the OR operation, but it's basically all zeros in the reference subarray. So the problematic data pattern is always, only when you're really close to the reference values, basically. And again, the authors looked at other sources of unreliability and try to see where the unreliability is coming from. And again, for example, the physical location of the rows activated plays a major role, as you can see in this plot very briefly. The rest of the analysis you can find again in the paper. So 20 minutes in, this is the conclusion. We can do actually the NOT operation in real chips you can buy today. So this is no fictional chips, they were bought in this hardware store. And we can do the NOT operation with up to 16 inputs and outputs at very high success rate, as we've seen in the plot. Also, the paper shown that we can do the AND and OR operation, as well as the NAND and NOR operation in the opposite subarray, basically. Also with very high success rates, depending on the data pattern a bit, as we have seen. So in conclusion, I would say the results in the paper are very promising and showing that we can actually use DRAM as a compute substrate already today, and that manufacturers have to do a bit of a job to make it more reliable, but the core ideas are already working. So that was basically the paper review. So let's go on to some of the strengths and weaknesses of the paper, and then go on to the discussion. So obviously, first strength of the paper is the first demonstration of a functionally complete set. Previous work only had a majority function, for example, which is not by itself functionally complete. So we achieved this by doing the multiple row activation across the subarray boundary, and then reusing the NOT gate basically in the sense amplifier to do an up to 16 output NOT operation. And we use the comparator function of the sense amplifiers to come up with an up to 16 input and 32 output AND and OR gates. Another strength is the very detailed analysis. So because the operations don't succeed at the 100% success rate, it's really important to study the factors impacting it. And I've shown you, for example, the number of destination rows plays a role in the success rate, but also the temperature was tested, as well as the different chip speed rate, do they affect it, and so on. And what I like the most is that they also included a lot of hypotheses, where I showed you some of them, which explain why certain parameters play a role in the success rate. And the last strength I have here is that it's all open source. The DRAM vendor infrastructure is open source, all the analysis is open source. So it's a good start for further research. So let's go on to weaknesses. It's also starting a bit into the discussion. My first point here is that while we have a NOT operation, basically the result of the NOT operation is in the other subarray, right? We use the NOT gate to basically get the, for example, if we want to negate the B, the NOT B will basically be in the other subarray. So I have a first question here for you, which I don't want to answer right now, but in the discussion, can we do with this data layout the XOR operation? It sounds like we should be able to do it because it's a functional complete set of operations, right? But maybe you can already think about what might be some of the problems we're facing with computing A XOR B, given that A and B are in the same subarray. And then we'll see why this is a problem. Another weakness is that only half of the data is computed upon on every operation because of the open bitline architecture I introduced in the very beginning. So only every second column is basically connected to one shared row of sense amplifiers. So we have to be a bit careful of the scheduling of the operations to really do an operation on a full row, because only every second cell will be connected to the neighboring subarray. Another weakness is that while we can do these very high input AND and OR operations, they're destructive, meaning that after we have performed the operation, both the input operands as well as the reference subarray is lost, right? We have overwritten it with the results. So we have to basically save the inputs or outputs beforehand in order to reuse them later. So if we have a bit more complicated Boolean expression we want to evaluate, X and Y have to be coming from somewhere else before. But we can do this, for example, we have seen in the lectures, I guess, row clone, which effectively clones rows. So it's not that big of a deal. And I think the biggest weakness, so it's not the weakness of the paper, but the biggest weakness of what we have right now is that it's not 100% reliable, right? So we've seen these plots. Some of these operations are at very high success rates, let's say 99% or so, but it's on an individual cell level. So a row consists out of 8 kilobytes of data normally, so 65,000 somewhat rows. And if each row, each cell basically finishes its operation successful with 99% probability, if the failures are basically uncorrelated, right, the probability of the whole row doing the operation successful is basically 0. So 0.99 to the power of 65,000 is a very small number. So it's a problem that is not 100% reliable yet if we want to run some real workloads on real existing chips today. And one other weakness here is that the statistics made in the paper are all on the individual cell level. So what you can see basically here is they took 256 chips and looked at some of the banks and do these operations basically, and looked on one cell. How often does this cell basically successfully do this operation? But they don't look at the whole row basically in a correlated manner. So it could be that, for example, each row has a success rate of 99.9%. But if all of the failures are uncorrelated in the row, so the 65,000 cells fail independently of each other, the whole row would never finish. But for example, if we would have some statistics on how likely is it for the whole row to finish successfully, maybe we could identify some of the rows already work 100% reliable because because it's basically, we have some cells here that can already do, for example, the AND operation 100% of the time. So it's perfectly reliable, but we can't tell if there's a whole row basically that can do this. So this was my strength and weaknesses part. So now we can get to the fun part, which is the discussion. So I want to ask as a first question, is this data location problem I teasered in the weaknesses part. So my question here is, given that we have X and Y in the top subarray, can we actually, using the operations I just described and they were introduced in the paper, can we do the XOR operation? So is there a way of performing a NOT operation followed by some ANDs and ORs to actually get XOR? So maybe let me quickly explain the problem again. When we negate, for example, the Y, it will be in the opposite subarray, right? So when we want to do the X XOR Y, which is basically decomposed in forms of NOT and 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 OR, is basically we have to do X and not Y, or sorry, the wrong way around. So not X and Y, or X and not Y. Can anyone see any problem evaluating this, given that X and Y are initially in the top subarray? Yeah, go for it.
So the problem might be that we never can have X and not Y in the same on the same side of the sense amplifier.
That's right. So is it actually functionally complete, the set of operations we introduced?
Unless we think of a workaround, it's not.
Yeah, I mean, it depends. The problem, what's the problem here? The problem is that X and Y are in the same subarray, right? So do you see any ways of solving this? So maybe what would happen if we had X and Y in both subarrays? Could we then compute the XOR of the both?
I think so, yeah.
Yeah, we could. But do you see any other solutions to this problem that we might do? And in general, the question is more like, does this generalize? So can we do every Boolean expression given that we have both all operands basically in both subarrays? Is it like generally true that given this like fact that it's functionally complete set of operations?
I mean, one idea would be to add a little bit of extra hardware to kind of connect the other side of the sense amplifier back to the same subarray and kind of control that.
I'm not sure if I got that. Okay.
So we can connect the other side of the the sense amplifier, the other side back to the same subarray with some extra hardware.
Yeah, exactly. That's basically what I have here. So by basically introducing for a bypass transistor, so it is basically just a transistor which we maybe can trigger by some DRAM command. We can just allow for row copies basically between two subarrays, right? And in this case, just if we had all the operands in one of the subarray, it would be functionally complete because we could do the NOT operation actually in the same subarray by just reusing the NOT gate and then copying it back up, right? So at this point, we actually have a functionally complete set if we have the operands inside just one subarray. But I think it's generally true that if we have all the operands in both subarrays, we're already functionally complete because it's just a scheduling problem if you have a larger Boolean expression to get the right results in the right subarray at the right point, right? Maybe we have to do some redundant computation of some of the operands, but we should be able to schedule a full Boolean expression basically up to the two subarrays if we have the duplicated operands. Exactly. So another discussion point I have is I showed you how to do the AND operation using the comparator function basically of the sense amplifiers. And my question to you is so I showed you the AND. So maybe let's start with how would the reference subarray look like for an OR operation? Can anyone imagine what values we have to basically put here in order to get an OR operation once we do the simultaneous row activation? Go for it.
I'd guess 0, 0.5.
Yeah, that's right. And do you see any pattern of, so we need this half charge cell here to make sure that if we have all zeros, basically the half is larger, right? And in all other cases, the compute subarray will be larger. So my question here is, what other functions can we do other than AND or OR? Is there like a whole class of functions we can do using this one?
Majority functions, but
for example, so we can do basically, can we do majority 3?
Yes. I mean, yeah, I think 3, 5. I mean, I don't think we can do majority. Majority 2 or 4 is not defined. So yeah, we can do majority 3, 5.
Exactly. But just for example, majority 3 would look like this, right? And majority 5. But is it a more general class of function? Like, can you imagine any other Boolean function with higher inputs that we could do? Like, how does this pattern generalize? So majority is basically, is the sum larger, more than half of the cells are activated, right? But can we express something like, is at least one cell activated or two?
Yeah, so we can do like a sum comparison.
Yeah.
In a way.
Yeah, that's true. So for example, we could say for 16 inputs, are at least 4 of these inputs larger, like 4 of these inputs set, right? So it's like basically compare the sum to some threshold values. And the problem here is it's a bit of an easy question, but we operated on 3 and 5 rows here. But if we're seeing we can only activate 2, 4,
and so on. But we can basically fix this very easily by just adding 0 cells to both sides, and it wouldn't affect the comparison at all, right? So we can also do, for example, 3 input AND and OR, as well as the majority 3 and majority 5 functions. So my next discussion point is a bit more general. In terms of unreliability, we've seen that these operations already work on existing hardware, right? But we have this unreliability problem. But can you maybe think of workloads where it's not a problem that some of the gates fail sometimes? So error tolerant algorithms or computation. Do you guys have any ideas if we could actually evaluate current processing using memory systems? On what workloads is basically the question.
I'm not sure, but maybe like in routing where we have, for example, when we send addresses and we have this specific CPUs or like devices which check for the payload, and we have some error correction algorithms.
For example, yeah, error correction algorithms would be one of them. So we have, but then you have to, I mean, if you want to have some error correction algorithm, you assume that you know the solution of what you want to compute, right?
Yeah, but when we're sending data, we already know what the solution is, and maybe just like the algorithms or have like specialized devices for that, and maybe we could use them there.
Yeah. Any other ideas of workloads that might tolerate some errors during the computation?
So maybe machine learning workloads that are already kind of pretty blurry in terms of exact numbers.
Yeah, that's true. So I first thought about the human brain, which is somewhat similar to neural networks. So the human brain also, if some of the neurons fail suddenly, right, you don't fall over or you don't die immediately. So it's somewhat error tolerant. And I think a few neurons die every minute. So it's actually built to tolerate some miscomputation. And yeah, true. I read some of the papers where basically neural networks are somewhat error tolerant, that even if some of the neurons basically miscompute or misfire or deactivated, still the classification result, for example, for image classifiers is still correct. And there are also some training techniques where actually they disable some of them and do some tricks in order to get it more error tolerant. So yeah, that's basically what I was thinking about. But also there's this whole space of, I think, probabilistic computing where the algorithms basically are operating on probabilities. And if some of the computation is a bit off the time, actually the result will be still very close to what if would have been done on reliable hardware. So maybe the next discussion point is, okay, we know that there are some workloads which would benefit from unreliable primitives, which we have seen. So we have a functionally complete set of them. But do you have any ideas on maybe how we could make these operations more reliable in general? So maybe on a meta level, like given some unreliable operation, is there some way to make it reliably magically? And the other part is, what is the source of the unreliability in the approaches I showed you? So here we start with the first. So is there a way? So assume we have, for example, a majority function which works more reliable than our NOT operation. Is there a way to basically combine very unreliable NOT gates with a more reliable majority operation, for example, in order to form a very highly reliable NOT operation? So given a NOT operation which works, for example, 90% of the time, and the majority function which works 100% of the time, can we build a NOT gate which works 99.99% of the time?
You're hinting on it pretty hard, but just adding multiple or having multiple the same NOT operation being done simultaneously, and then majorating the solutions to that to get a pretty high chance of having the correct NOTs come out.
Right. So exactly, if assuming we have a very high reliable majority function, we can basically get all the other operations up to the same level by just doing it redundantly and then majoritying, right? And in terms of the sources, maybe let's discuss it a bit more generally. What are the sources of the unreliability? So what we have seen is that, for example, for the AND operation, it fails for certain data patterns, right? So why might this be the case? Actually, so what are some of the reasons for the comparison to completely fail in some percents of the time?
because we kind of use the DRAM circuitry in a way it was not created or intended to work. And yeah, that's, I mean, probably that's the reason. And I don't know, a way to fix it would be change the manufacturing process, or I don't know.
Yeah, it's true. But what would you fix in the manufacturing process? It's the next question.
I don't know.
Okay, so I don't know either. So I think this is like a bit of research missing to actually get this really reliable. And I think there's also some follow-up papers where Ismail or Zafari discusses, for example, using basically trying to get rid of the state where you have the reference subarray very close to the values in the compute subarray by basically copying the compute values twice. Yeah, so there can't be the state basically where you're too close to it. For example, if you have a 2-input AND operation, the problematic case is where you have the 1-1, right? But if you copy it before computing upon it, basically a full 1 case is 4 ones. And now if you have the reference subarray set to, for example, 3 ones only, so you don't need the half-charge cell anymore, basically the voltage difference increases and it gets more reliable. So there's a bunch of research trying to fix this in current chips, but also, trying to figure out what to change in the manufacturing process, or trying to get this more reliable, so we can have a full 100% reliable processing using DRAM as system. So my next question is, do we actually need this FRAC DRAM? So I showed you that in the reference subarray, for example, for the 2-input AND, we need this half-charged cell. And I want to discuss, is this actually needed, or is there some other way where we can have a reference subarray and a compute subarray without needing these half-charged cells? Because, for example, one disadvantage is a refresh wouldn't survive, right? So after the refresh is finished and the row got activated once, the value is reset to either 1 or 0. Yeah.
So what if we, instead of having one fully charged and one half charged, we have three full charge and one uncharged cell?
Exactly. So we can also do this by because we have this end-to-end activation pattern, right? Or we could just put duplicate the data before. But basically, I think what you said is true. We don't actually need it. We can just do this 3-to-1. We will get the same average on the bit line, and the result of the comparison, will basically be the same. So actually, we don't need the FRAC DRAM, but it wasn't shown in the paper, so I thought it might be interesting to see if how this affects. Because for example, in this case, all the cells would survive a refresh, right? So it has some advantages also. And this, my last discussion point, is about how we can schedule the operands, and in general how we would build like a full processing using memory system with it, because the problem is the results are overwritten, right? So how could we build this to a full system where, like, in general, what do you guys think about how we should build a full system using these primitives, and where should the operands be kept, and how does it play with the unreliability? So just thoughts in general about how we can build a real system from it. Yeah. Go for it.
If you have the resources, partition the DRAM system so that half of the DRAM system, let's say, is used for memory storing and another half for computation.
Yeah, I think that would work. And I think, also it would make sense because we've seen this unreliability problems, that maybe we profile the chips first to figure out certain areas where they may be working more reliable than others, and then storing the data where it's basically not good for computation. And we can store and compute where the operations already succeeds at a high probability. So I think that was it for my presentation. Thank you for listening.
Should I say something? This is my paper. I like it, objectively. Sorry? Both. Yeah, I think this, when I was doing it, I was really enjoying it, because it was, as Christian showed, it was a theorem. Like, we were going to the blackboard and try to draw things and understand, like, how do we enable things, and or like, why can't we do XOR, etc. So it was really fun when doing it. Yeah, I wish I could achieve 100% of success rates, but I guess it's also good for future work. because there are a lot of things going on, especially in PIM. And I believe PUD is one of the promising paradigms in PIM. So there are a lot to do, as Christian showed, like there are problems. I'm not denying it, those weaknesses. I believe there are weaknesses from my side, and also that we're using real DRAM that are not intended to do such things. So yeah, if you would like to work on these things, feel free to reach me anytime. And yeah, there are a lot of things to do here still. Yeah, that's what I would like to say.
So I guess that concludes today's session. And just a reminder for everyone to fill in the quiz and the evaluations. Thank you.
Yeah, kind of.